If you want to propose a radical idea in aerospace, you submit it to the Journal of the British Interplanetary Society. It is a peer-reviewed fortress, notoriously rigorous and rarely prone to speculation. So when they publish a paper concerning an object called 3I Atlas, pronounced 3I Atlas, we have to pay attention. At first glance, this looks like a typical interstellar fragment. It is a dark, irregular, icy rock that originated from the galactic thick disk. The thick disk is an older, metal-poor region of our galaxy. Because of its appearance, the mainstream scientific consensus quickly classified this new arrival as a standard inert comet. It was assumed to be an ordinary, passive chunk of ice and rock pulled into our solar system by gravity. But an independent researcher named Kevin Thorsen Baird compiled a physical telemetry divergence analysis that completely contradicts that mainstream consensus. This analysis mathematically compares the expected natural trajectory of an object to its actual recorded movements. Baird's peer-reviewed paper exposes 3 distinct, mathematically verified anomalies in the data. These are physical and chemical behaviors, proving the object cannot possibly be a natural formation. If the data confirms these 3 anomalies, the mainstream cometary model fails, meaning the object currently leaving our solar system is a machine. To understand the first anomaly, we have to look at the baseline composition of natural protoplanetary bodies. In nature, heavy metals like iron and nickel always condense and mix together during formation, usually at a ratio of roughly 1.8 to 1. This spectral analysis line chart shows the chemical makeup of 3I/Atlas. It reveals a massive, unexpected presence of neutral nickel-62. But look next to it. There is an absolute absence of iron, down to the detection limit, breaking the standard rule of natural accretion. Natural formation mixes these elements indiscriminately. Completely separating iron from nickel suggests the object has undergone an industrial-grade refining process. Baird argues this points to a specifically engineered alloy of nickel-62. This isotope has the highest binding energy per nucleon of any stable nucleus, rendering the material maximally resistant to radiation damage during a multi-thousand-year interstellar transit. The second anomaly was captured by this specific instrument, the Hubble Space Telescope. Hubble identified a massive 400,000-kilometer sunward-pointing feature, an anti-tail jet pushing out directly from the object toward the sun. In standard gas dynamics, this should be impossible. The solar wind pressure creates a massive drag that should arrest any neutral gas outflows trying to push upstream against it. This vector diagram shows the force required to pierce the solar wind. To penetrate 400,000 kilometers upstream, the jet's dynamic exhaust velocity must exceed 447 kilometers per second. Natural thermal sublimation maxes out at a mere 0.5 kilometers per second. There is only one known mechanism capable of generating this extreme velocity. It requires a high-specific impulse ion or plasma propulsion system. High-specific impulse refers to engines that use electrical energy to accelerate propellant to extremely high speeds. The magnitude of this force points toward a high-powered engine actively countering the solar wind, far exceeding the physical limits of passive outgassing. The final anomaly becomes clear when we focus on the coma's visual structure by applying a rotational gradient filter to the raw Hubble imagery. A rotational gradient filter is an image processing technique that isolates faint, fine structures hidden within bright, diffuse halos. When we apply this filter, 3 distinct, sharp, cyan plasma jets emerge, piercing through the visual noise of the outgassing. This is a geometric overlay, measuring the angles of those jets. They form a mathematically perfect equilateral triangle, spaced exactly 120 degrees apart with 0 variance. Contrast this extreme precision with natural cometary venting. Natural outgassing is driven by stochastic surface fractures, resulting in chaotic, asymmetrical patterns. Maintaining 3 jets at such an exact 120-degree orientation suggests a spin-stabilized venting system, a level of control that natural surface fractures simply cannot replicate. When you synthesize the chemical purity, the extreme exhaust velocity, and the perfect geometry, you arrive at Baird's concluding model for 3I ATLS, the hybrid engine hypothesis. This hypothesis reveals the true internal structure of the object. It is a solid, geometric machine core, hidden safely beneath a harvested shell of water and ice. The system uses a dual-mode mass loss process. The outer ice sublimates isotropically to cool the 4.2 Kelvin core, acting as an ablative shield against the heat of the sun. Isotropic sublimation means the ice evaporates evenly in all directions. This is a schematic showing how the engine actually thrusts. A tiny fraction of this harvested water is magnetically collimated into those high-velocity cyan jets for deliberate steering. The object is currently on a specific trajectory, preparing to graze Jupiter's Hill sphere. The Hill sphere is the region of space where a planet's gravity dominates the motion of passing bodies. Here, the probe will execute a deliberate O-berth maneuver, firing its engine deep within the gravity well to lock its path into a tuned interstellar corridor. This theory faces a looming test in May 2026. Baird has issued 2 live falsifiable predictions: an abrupt drop in outgassing, known as valve closure, and a deliberate velocity correction called the z-axis shift. The peer-reviewed paper has successfully identified the historical anomalies, but the live predictions will be the final definitive proof of alien technology.